Now, we know that in the distributed system, there are several resources which are available in a particular system. And we must have a resource allocation policy, which ensures the exclusive accesses by a particular process. Now, as we know that the system is consists of a finite number of the units of the resource types are concerned. For example, it may be printer, it may be tape drive, it may be disk drive, it may be CPU, etc. So there are multiple concurrent processes. Normally, they have to compete with themselves to use these resources. So in this particular situation, the sequence of event required to use the resources by a process must follow some regulation, some rule. So what are the things which the processes has to follow? The first rule is the request. So what is the request? So the process, first of all, it makes a request for the resources, whatever it wants. If the requested resource is not available, just because that it is being used by another process, the requesting process are put into the wait state until the requested resource is allocated to it by a particular system. Now, if the system has multiple units of the requested resource type, the allocation of any unit of the type will satisfy the request. There are certain resources, and the resources are having many units, and that resource is being requested by a particular site, and it is having many units. And one unit is being served to another resource, another site. So the site which has requested for one unit, and if it is available at the resource site, it can be allowed. It can be allowed. So if multiple unit of the requested resource type is available, then the allocation of any unit of that type will satisfy the request. Now, a process may request as many as unit of a resource as it requires. It is not necessary that it will be asking only for one unit of that resource. It may be asking for, it may be possible that it may be asking for many units of the resources. So it requires, it has to be done with the restriction that the number of the units which are requested must not exceed with the total number of the units of that resource. Suppose that particular resource is having 2 units and particular site is asking for the 3 units and the available is only 2 units. So it should not be. The resource policy should be, there must be some restriction so that the number of the unit which are being requested must not exceed the total number of the available unit. Now the second one is allocate. Now the system allocates the resource to the requesting process as soon as possible. Whenever it is requested, it is required that it should be allocated. So what it does, the system maintains a table in which the records whether the resource is free or the resource is allocated, or and even though if it is allocated to which process it is being allocated, all these things are maintained in that particular table. Now, if the requested resource is currently allocated to another process, suppose there is a process which is requested for a particular resource, and that requested resource is currently allocated to another process. Then what happens? Then the requesting process is added in the queue of the processes waiting for that particular resource. It may be possible that other resources are also waiting. So it will be put into the queue. Now, once the system allocates the resource to the requesting process, that process can exclusively use the resources by operating on it. So that is the meaning of the allocate. And the third one is the release. After the process has finished using the allocated resources, it releases the resource to the system. So the system table, as I told you, that it is maintaining the records. So that record must be updated at the time of allocation as well as when at the time of release also, just to reflect that what is the current status of the availability of that particular resource. Now, the request and the release of the resource, you can call it is called system calls. Uh, System calls such as request and the release for the devices, open and close of the files, allocate and free of the memory spaces. And out of these three operations, request, allocate, and the release, out of these three operations, this is the allocate operation. Allocate is the only operation that the system is going to control, or which is under the control of the system. And the other two, request and the release, are the two operations which are initiated by the process. And allocate is the is an event, is the process. Allocate is the only operation which is under the control of the system. So with this pattern of request, allocation, and the release of the resources, if the total request made by the multiple concurrent processes for the resources of a certain type, if it exceeds the amount available, there are many sites and they are requesting for the resources, and the resources which are available. Now all the are requesting, and the total number of the request for using the resources, number of units of that resources, if it is more than it is available, then we must adopt certain kind of a strategy so that we are able to assign the resources in time in a certain order. So what is necessary? The important thing is that the care must be taken, so that the care must be taken in designing the strategy, in framing the policy, so that it is not going to cause any kind of deadlock. So what is actually the deadlock? Deadlock is a situation in which competing processes prevent their mutual progress, even though no single one requests more resources than that are available. So it may happen that some of the processes that entered into its waiting state because the requesting resources are not available at the time of the request, so it will never again change its state because the resources that they have requested are held by other waiting processes. So this situation is called deadlock, and the process involved in that is said to be deadlocked. So hence you can say that deadlock is a state of a permanent blocking of a state of the process, and each of which is waiting for an event that another process is the set which is going to cause it. So all the processes in the set block permanently, because all the processes are waiting, and hence none of them are able to, none of them will ever cause any kind of event that could wake up any of the order of the members of the set. So as far as the deadlock situations are concerned, it can be very well explained by a certain example. Suppose that we have a system in which we have two tape drives, T1 and T2, and the resource allocation strategy has been framed in such a manner that the requested resource is immediately allocated to the requester. Whenever a request comes, it should be immediately allocated to the requester. So it should be allocated to the requested if it is free. If it is not free, it will be in waiting, but if it is free, it should be allocated. This is the strategy, this is the policy. So now again, suppose that we have two concurrent processes, P1 and P2, which are making a request for these tape drives, that is T1 and T2. And they are making a request in a particular manner. What is that manner? Suppose the first situation is P1 is going to request one tape drive and the system allocates that T1 to it. The first situation. The second situation is P2 is also requesting for one tape drive and the system allocates T2 to it, because it is the policy that whenever request is coming and it is free, resource is free, immediately allotted. Now the third third event is P1 is again requesting for one more tape drive, and since the available tape drives were two, T1 and T2, one is allotted to P1, another is allotted to P2, and now P1 is requesting one more tape drive. So what it will do, it will enter into the wait state because no tape drive is presently available. So, and the next situation, in the next situation, the P2 is again asking for one more tape drive. So it is also going to be into the waiting state because no tape drive is presently available. So is it not a deadlock situation? It is going to create a deadlock situation. So now, if P1 and P2 will now, the P1 and P2 will have to wait indefinitely because P1 will not release T1 until it gets T2 to carry out its design, to carry out its task, and P2 until the P2 has released T2. Whereas P2 will not release T2 until it gets T1. Since P1 is in requirement of T1 and T2, and P2 is also in requirement of T1 and T2, and T1 is allotted to P1 and T2 is allotted to P2. So until unless any one of these processes is not going to release any one of the resource, either T1 by the P1 or the T2 by the P2, they will be in the deadlock situation. Now, what can happen? That the request made by these two processes are totally legal because they are in demand, they are requesting because they are in work. So it is legal because each one is requesting for two tape drives. So, and the total tape drive which was available earlier was only two. So this deadlock problem occurs. This is the problem of deadlock which occurs because the total request of both processes exceeds the total number of the units which are available in the form of a tape drive. So the resource allocation policy should be such that it immediately allocates the resource of the request if the resources are free is not valid. So meaning thereby we have to do something so that uh, we are able to avoid the deadlock situation. So in the context of deadlocks, the term which is known as resources, it is applied only not to the physical objects that such as tape, disk drive, printers, but it is also to the logical objects such as uh, records which are available in the database, files, tables, semaphores, etc. So these resources should permit only the exclusive use by a single process at a time, and it should not be preemptible. So, and now what is preemptible? A non-preemptible resource is one that cannot be taken away from a process to which it was allocated until the process voluntarily surrenders it or releases it. So if it is taken away, it will going to cause the ill effect on the computational ability or whatever is computational is going to be performed by the process. For example, if there is a printer is a non-preemptible resource because taking the printer away from a process that has started printing but has not completed its printing job and giving it to another process, so that is going to produce the printed output containing a mixture of the output of the two different processes. So this is certainly not acceptable. So that is the meaning of non-preemptible resource. Now, what is the necessary condition for the deadlock? You have already studied in the operating system that there are certain necessary condition for a particular deadlock. The first is mutual exclusion condition. What is that? If a resource is held by a process, another process requesting for the resource must wait until the resource has been released. This is the mutual exclusion condition. The second one is hold and wait condition. Processes are allowed to request for the new resources without releasing the resources that are currently holding. Suppose there is a process which is already few resources has already allocated to that, and that process is again requiring some more new resources. So in that particular, and whatever resource it is asking, requesting, besides the allocated resources, that is being used by some other processes. So the processes are allowed to request for the new resources without releasing the resources that are currently holding. So that is going to give the condition of the deadlock. The third one is no preemption condition. A resource that has been allocated to a process because process becomes available for the allocation for another process only after it has been voluntarily released by the process holding it. If some resource is being required by a certain process and that resource is already available with allocated to some other process, until unless it is not going to release it voluntarily, it is going to be the deadlock situation. And the fourth is the circular wait condition, in which two or more processes must form a circular chain in which each process is waiting for a resource that is held by the next member of the chain. A is requiring B, B is requiring C, A is requiring a resource which is held by B, B is requiring a source which is held by C, C is requiring a source which is held by D, and D is requiring a source which is held by A. So it is framing a chain. Now, out of these four conditions, all the four conditions must hold simultaneously in the system of the deadlock. If you can say that system will be in deadlock or the deadlock has occurred, all the four conditions must hold simultaneously. If any one of them is absent, no deadlock can occur. If any one of these are absent, the deadlock cannot occur. So out of these four conditions are completely independent, because the circular wait condition, as far as the circular wait condition is concerned, what is the meaning of circular wait condition? This implies the hold and wait condition. So out of these four conditions, somehow they are interrelated, and they are also useful to consider them separately to devise the method which is going to frame a deadlock prevention algorithm. So, but before we go into the algorithm of that, let us look for the deadlock modeling. And deadlocks can be modeled using a directed graph. So there are different terminologies which you already know, but it's my duty to explain that the first terminology which is used in the deadlock modeling is the directed graph. You know what is directed graph? Directed graph is represented in the form of a pair, which contains it's a tuple in which one is called n and another is called e, where n is the non-empty set of the nodes and e is the non-empty set. It is a set of directed edges, and that is why it is called the directed graph. So if a directed edge in the form of an ordered pair, that is AB, it means there is an edge from A node to B node. Then we have a path. Path is a sequence of the node from A to B, C, D, in a directed graph, such that AB, BC, CD, DE, like that. So path contains at least two nodes. This is a path. This is an edge, and path. If there is a path in between A and B, there must be at least one edge in between A and B. Then what is cycle? Cycle is a path whose first and the last nodes are same. For example, it is framing a cycle. So F to A to B, B to C, C to D, D to E, E to F. So this is constructing a cycle. There is another cycle. B to C, C to D, D to E, and E to B. So the starting node and the end node, last node, if it is same, it is going to frame the cycle. Reachable set. The reachable set of a node A is the set of all nodes B such that there is a path. A path is going to exist from A to B. So that is called the reachable set. If you are able to reach from A to D by this path, it means these A, B, C, D are the reachable set. Then what is not? Knot is a kind of a it's a kind of a graph in which that will be containing one or more cycles. So knot is a non-empty set of nodes such that the reachable sets of each node in K is exactly the set, the value of K. So knot contains always one or more cycles. So as far as this example is concerned, whatever has been shown here, now in this example, the graph has a nodes A, B, C, D, E, F. These are the nodes. There is a edge from A to B, B to C, C to D, D to E, E to F, and F to A, as well as E to B. These are the edges. So edges are represented in the form of a ordered pair A to B, which shows that there is a path from A to B, and that is why it is represented. Since it is represented by directed graph, so there is a path, there is an edge from A to B. As I told you that this particular directed graph is having two cycles. One is from A, B, C, D, E, F, A. Another cycle is B, C, D, E, B. This is another cycle. So there are two cycles in this particular graph. Now, as far as the deadlock modeling is concerned, for deadlock modeling, a directed graph called the resource allocation graph, it is used uh, for data deadlock modeling. This directed graph is represented or called resource allocation graph, whose purpose is to in which all the nodes as well as the edges are partitioned in two types, resulting in the different graph elements. And what are those graph elements? First is the process node, second one is the resource node, third one is the assignment edges, and fourth one is the request edge. So these are the certain uh, uh, parts of the resource allocation graph. So first of all, let us discuss about the process nodes. What is process nodes? So process node represents a process of the system, and it is represented in the square. Sorry, it is represented in the form of a circle. This is P1. P1 is a process and it is represented in the form of a circle. So in this resource allocation graph, it is normally represented in the form of a circle with the name of the process written inside the circle. Then we have a resource node. Whatever resources are available, that is represented in the form of a rectangle. And within that rectangle, the name of the resource is being written along with how many units of that resources are available. In R2, we have 1 unit, so it is represented by single dot. R1 has, it's a kind of a resource which contains 2 units, so it is represented by 2 dots. R3 is another resource which is containing 3 units, so it is represented by 3 dots. Now, assignment edges. What is assignment edge? An assignment edge is a directed edge, such as from P1 to R1. It's a directed edge from the resource node, from a resource node to the process node. Assignment means whenever this resource is assigned to process P2, it is represented by a particular edge. So that edge is called assignment edge because it represents that this is the resource and this is the process. And since the edges are from R2 to P2, it says that R2 is assigned to P2, means R2 resource is assigned to P2 resource. Similarly, R1 resource is assigned to P3 resource. R1 resource is assigned to P1 process, and so on. The request edge. Request edge is an edge which is a kind of a request which a process used to send. Suppose process P1 wants want to use the resource R2, so it will send a request message to this resource. So this edge is called the request edge. So we have one request edge from P1 to R2. There is another request edge from P2 to R1. There is no, only two request edges are there, P1 to R2 and P2 to R1. And assignment edges are R2 to P2, R1 to P3, and R1 to P1. So this is the explanation of process node, resource node, assignment edges, and the request edges. Now here, this resource allocation explanation has been done. That Pi represents a process named as Pi. It is a resource. A resource is having 3 units in the system. If R1 is assigned to P1, so it is process Pi is holding the 1 unit of resource Rj, and Pi is requesting for a unit for the unit of the resources Rj. Now, how this graph is being constructed. So, constructing a resource allocation graph. A resource allocation graph actually it provides the overall view of the process holding or process waiting for the various resources in the system. That is why it is necessary to draw the resource allocation graph. So this graph, the dynamics of this graph is going to change very abruptly as the process is going to request or the resources are being released by the processes. Whenever there is a request, an edge will be inserted. Whenever there is a release, so assignment edge is going to be omitted. So meaning thereby it is going to be changed dynamically as the processes are requesting and the releasing the resources. So when a process Pi requests for a unit of a resource type Rj, a request edge is called Pi Rj is inserted. When a request is fulfilled, when the request is fulfilled means it is allowed and Rj is allocated to process Pi, then the request edge Pi Rj is transformed to an assignment edge. The edge which is coming as a request edge, that is changed into a assignment edge, and that edge will become Rj Pi. And when Pi releases the Rj after completing its critical section, it is releasing Rj, the assignment edge is deleted from the graph. So this is how we are going to construct the resource allocation graph.